Omron Automation Americas presents Introduction to Machine Vision Lensing.
Hello, and welcome to Omron Automation Americas. My name is Jeremy Orbach, and I'm the Automation Training Leader for all things machine vision here at Omron. We are here at our corporate headquarters in beautiful Hoffman Estates, and are excited to virtually invite you into our facility. Today, we will be introducing the concept of machine vision optics and taking you through the basics of lenses, how to select a lens, and the different resources available to you for supporting your machine vision needs. This video is designed as an educational introduction to our machine vision courses.
We begin by discussing our agenda for this video. We will highlight the function and purpose of lenses in machine vision, discuss different types of lens technology, how to differentiate lenses, terminology, as well as how to properly select a lens. The function and purpose of a lens is simple. It acts as the interface between our camera and inspection object. The goal is to ensure projected light is reflected at the right clarity and brightness to be able to make a judgment. While the camera itself controls things like shutter speed, gain, and white balance, the lens dictates two important factors in creating a high-quality image. As we can see in this slide, there are many options available for lenses. We can also see different types of filters and adapters available. When we want to understand the specifications of a certain lens, we must pay attention to both the focal length as well as the aperture. The aperture controls how much light is allowed to pass through the lens onto the image sensor. It is defined by what are known as f-stops. The larger the f-stop number, the smaller the opening during our image acquisition step. Aperture dictates our depth of field, which we will discuss later in this video. The focus ensures we can clearly see the inspection object, and the edges are clearly defined. Some lenses have a fixed focal point, which means the focus cannot be adjusted and requires a very specific position for the inspection object to be in focus. Other lenses have a variable focal point, which we will also discuss later. There are 5 main connection interfaces between the lens and camera. Most machine vision lenses have a threaded portion that can be screwed into the camera. S-mount, otherwise known as lipstick lenses, are very small and designed for extremely confined inspection environments. C-mount is the most common lens connection, while CS-mount is a C-mount lens that is 5 mm closer to the image sensor. M42 is a large format lens for machine vision applications, whereas F-mount is the same format Nikon uses for connecting DSLR lenses to the bodies. Omron has solutions available for all connection types except F-mount. As the C-mount standard is the most common in the industry, let's understand what defines a C-mount lens. First, the diameter of the connection is 1 inch or 25.4 mm, with 32 threads per inch. The distance between the rear of the lens and image sensor is 0.69 inches or 17.5 mm. Recall that the CS mount lens is identical to this, except the distance is 12.5 mm instead of 17.5 mm. This means we can use a C-mount lens on a CS mount camera using a 5 mm extension tube.
It is important to understand that while most vision systems comprise of a separate controller, camera, and lens, our FHV7 smart camera combines all of these into a single piece of hardware that can be customized to each application. While the FHV7 supports standard C-mount lenses, specialty autofocus and liquid lens options are available that use a connection type that is unique to the FHV7.
We mentioned that there are options available for both fixed and variable focal lenses. A majority of the time, a fixed focal lens is used for applications where the object is always appearing at a set distance from the camera and will not change. However, understanding that variable focal lenses allow for quick adjustments to focus, it is possible to create an inspection where the inspection object sometimes appears closer or further away from the camera. Omron has a wide variety of lenses for both fixed and variable focal point applications. If you are new to industrial machine vision, you likely have not heard of liquid lens technology. This technology is available in many of Omron's smart camera and vision sensor lines, including the FHV7 and Microhawk F-Series smart camera. As we can see from the image, it is a single lens membrane filled with fluid. Using changes to voltage applied directly to the lens membrane, it can expand or contract to make extremely quick changes to focus without requiring any mechanical adjustments. When most folks think of a standard mechanical lens, many assume it is a single piece of glass in an enclosure. In fact, most lenses are not a single lens. The lenses we see are actually comprised of a series of different lenses that move inside the lens enclosure. Different combinations of single lenses are what produce different lens specifications and types. The types of mechanical lenses we will be discussing are CCTV, telecentric, zoom, macro, and wide-angle lenses, which support the solution of many machine vision applications. Before we dive into the different types of lenses, we must understand the basics of vision terminology. This slide provides a quick reference to all the different criteria necessary to properly solve a machine vision application. The first thing we must pay attention to is the focal length, which is how we ensure our inspection object is actually in focus. It is defined as the distance between the center of a lens and the focal point. As our focal length increases, our magnification also increases, but our angle of view becomes narrower, creating a smaller field of view. As our focal length decreases, our magnification decreases and creates a wider angle of view to create a larger field of view. We can see this clearly on this slide. At 12 millimeters, we are able to see the entire PCB array in our field of view. But as we increase it to 35 millimeters, we are now zoomed into a smaller area of the PCB and thus create a smaller field of view. At 50 millimeters, we can now see the circuits very closely and have a very limited field of view, but have enough inspection data to begin making judgments on the quality of the circuit. We must keep in mind the focal length will dictate the level of clarity we see, as well as the detail necessary to perform our judgment. Working distance is defined as our distance between the edge of the lens and the inspection object. Working distance is necessary to calculate early during the solution of the application, as there are frequent limitations in the environment that may prevent a very long working distance. Camera distance is defined as working distance plus the length of the lens, or the distance between the front edge of the camera and the inspection object. When selecting a lens and using Omron's optical charts, we must use camera distance rather than working distance to properly select the lens. As mentioned when we were discussing aperture, depth of field directly correlates with the size of the aperture. The depth of field is defined as the focus range in front of and behind our inspection object. The larger a depth of field we have, the most in focus objects will be as they move closer or further away from the camera. In addition to aperture, extension tubes can be used to reduce the depth of focus based on the length of the extension tube. In these images, we can see the direct correlation between the aperture and the focus of the LEDs. On the left side, we can see the three color LEDs at slightly different distances from the lens. When our aperture is large, only the red LED is in focus, whereas the blue and green LEDs are out of focus. As we reduce the size of the aperture, we can create a larger depth of field to ensure all three LEDs are in focus. As there are larger variances in the distance of the inspection object to the camera, it is important to consider the depth of field to ensure the final image can have a repeatable judgment made on it. Pixels are the fundamental building block of an image and are usually red, green, or blue. 3D arrays of pixels create digital images as we see them. The resolution of the image is the relationship between the size of our field of view and the number of available pixels in the image, and can be calculated by dividing our field of view by the total number of available pixels. A 0.3 megapixel camera has 640 pixels by 480 pixels, creating 307,200 total effective pixels. From consumer technology, an HDR TV, known as 1080p, has 1920 pixels by 1080 pixels, creating 2,073,600 total effective pixels. As our resolution increases, our inspection time increases due to the amount of pixels needing to be processed. This can create a bottleneck in our process if we choose a camera that has higher resolution than the speed at which we want to inspect, and needs to be factored in when applications are moving in front of the camera. The field of view is defined as the dimension of the area we want to inspect, sometimes known as our field of vision. Focal length and working distance will both affect our field of view size and must be taken into consideration when deciding how to pick a lens. If the working distance is limited, we must adjust our focal length to ensure the right field of view is visible. Extension rings and tubes allow us to change the focal length range and increase magnification without having to replace our lens. They are installed between the lens and camera and will shorten the working distance. We will reference extension tubes at the end of this video when using Omron's Vision Accessory catalog to choose a lens. As we can see, without any extension tube at a set focal length and distance, we can see a large field of view on this remote control. As we add extension tubes, we can see the magnification begins to increase very quickly, reducing our field of view. At 80 millimeters, we can begin to make judgments on the surface quality without ever having changed our focal length or distance. A rear converter lens is similar to extension tubes, except the working distance does not change. If we have a constrained working distance, the only option available is to adjust the camera distance and use a rear converter lens to adjust our field of view size. Keep in mind that brightness is sometimes influenced by usage of rear converter lenses and are costlier than extension tubes. Now that we understand the basic terminology for machine vision lenses, let's dive into the different types of lenses themselves. While there are more types of lenses than what are shown in this slide, we will be focusing on these lenses as they comprise the majority of lenses you will need to know to solve your machine vision application.
Beginning with our entry-level options, CCTV lenses are used for low-cost applications that do not require accurate measurements to be performed. Many options are available, including variable focus and aperture, but are limited in application use due to barrel distortion and a lack of vibration resistance. Macro lenses are used to allow for very short working distances, 100 millimeters or less, and are less influenced by distortion and vibration than CCTV lenses. Keep in mind that because we must be 100 millimeters or less from the inspection object, we will have a limited field of view as well as a limited ability to focus.
To understand barrel distortion, it is important to visualize the difference between the same inspection object using both a CCTV and macro lens. As we can see on the left, the edges of the image are much clearer and appear more in line as compared to the right. It should become very apparent why CCTV lenses should not be used for measurement, as the effect of barrel distortion is clearly highlighted here. However, macro lenses may not be accurate enough to perform a measurement. Telecentric lenses are the cutting edge of lenses designed for micron-level accuracy measurements. Used in Omron's automated optical inspection line, when combined with high-resolution cameras, we are able to measure distance and color up to a 5-micron accuracy. This allows us to make judgments around the quality of a solder joint and flag for solder defects the human eye could never pick up upon. As the size of the lens must be larger than the field of view, the footprint of this lens is very large and requires a large working distance. However, no barrel distortion is present due to the lens being the actual size of the field of view. Telecentric lenses are among the highest cost and highest value and are primarily designed for the mission-critical applications such as aerospace and military. As we can see from this slide, looking at our inspection objects in the left column, we can see the distortion present using conventional lenses. If our goal is to measure the distance between each cylinder, we would be unable to do this accurately with a conventional lens. The same goes for measuring the diameter of the hole cut out in our inspection piece or measuring the size of each step. This slide shows us how our measurements would be influenced if we use a conventional lens instead of a telecentric lens. If we attempt to measure the width between each end pin on the connector component, using a conventional lens we read 8.28 millimeters. We can see the distortion present along the edges. Using the telecentric lens, we read 8.53 millimeters and can verify there is no distortion present. A zoom lens is the last type of lens we will discuss, as it allows us to adjust the zoom level without having to adjust our working distance. This allows for quick changes in magnification, but have very limited applications in the world of machine vision automation. Keep in mind that zoom lenses are significantly larger than non-zoom lenses, which can limit their usage and are significantly higher in cost than non-zoom lenses. We should now understand the basics around the types of lenses and terminology used. Omron has published a vision accessory catalog, which is available directly through Omron's website. This catalog supports the specifications around every lens and can support the decision-making process around which lens would be most appropriate. We can see a selection of lenses on this slide, as well as their associated part numbers, which are referenced throughout the catalog. On page 70 of the Vision Accessory catalog, we can see the recommended lens charts for all FH and FC cameras. To properly narrow down the series of lenses you will need for your application, you must first know the resolution or model of camera you will be using and whether a standard lens, telecentric lens, or vibration and shock resistant lens is necessary. For example, if we know that we want to perform a measurement using an FH-SC04, we see the VS-TEV series is recommended, and the details of this lens series are on page 79. We can also see that for many of the lenses, optical charts are referenced, which allow us to identify the exact model number of the series to solve our application. Here we can see the recommended lenses for higher resolution cameras, and combined with the previous slide, acts as a quick reference to identify the series of lenses recommended and tested by Omron to solve your application. We can see from this slide that the FH-SC12 does not support telecentric lenses, which the FH-SCX12 does, whereas the FH-SCX12 does not support vibration and shock resistance when the FH-SC12 does. Here is another reference when utilizing C-mount lenses on the FH-V7. As we mentioned during our introduction to the FH-V7, there are proprietary lenses unique to the FH-V7 that are not referenced here. We should now understand how to reference the Vision Accessory catalog when identifying the series of lens Omron recommends. To narrow down the lens series to an exact model of lens, we must understand the usage of optical charts and what to do when optical charts are unavailable. Many lens manufacturers have created online lens selectors, and a quick online search will provide many different calculators that require different variables to identify the correct lens. We need to consider this information before we begin using these calculators. When utilizing non-Omron lenses, it is necessary to know the physical size of the pixels and the image sensor size. Using these two variables, we can calculate the effective number of pixels, which is also sometimes necessary. This information is input directly into the lens calculator, and a lens model is recommended. However, when utilizing Omron lenses, we only need to know the camera model we want to use, the size of the field of view, the working distance, and camera distance to properly select our lens. This is what Omron's optical charts look like. The y-axis is the camera distance, the x-axis is the field of view, and the T number indicates whether an extension tube is necessary and the size of the extension tube. Each color line corresponds to a different lens, shown in the legend. Once we have selected our camera and lens series, we can navigate to the associated optical chart to narrow down to a specific lens. We can see at the top the supported cameras, as well as the series of lens being identified. Using the data from our application, we want to see where the data points meet. In this example, we can see that our field of view is 400 mm by 290 mm. We always use the smaller of the two values for the x-axis. As our working distance is 1000 mm, we must convert this to camera distance to properly locate the correct lens. In this case, we add 50 mm to working distance to calculate 1050 mm. We can see where the intersection occurs between 1050 mm on the y-axis and 290 mm on the x-axis. As we can see, the intersection is closer to our yellow line, which references the SV1214V or 12 mm version of this series. As the intersection is closer to the yellow line than the black line next to it, no extension tube is necessary. However, if we saw the intersection closer to the black line instead of the colored line, an extension tube will be necessary to get the right field of view. When utilizing lenses from other manufacturers, ensure you have access to all the necessary variables for each lens calculator and input those values into the calculator. This will immediately recommend a lens based on the company hosting the lens selector. Omron cameras work with a wide variety of different lens manufacturers, and if there are any questions around this, feel free to contact your local Omron Vision expert or the manufacturer of the lens. When available, it is ideal to use Omron's optical charts due to how simple they are, but realize there are many different lens manufacturers that have compatible lenses with our cameras. Therefore, we make our recommendations due to each one having been tested for quality control and reliability, and are supported directly by Omron. If non-recommended lenses are utilized, we cannot guarantee the same reliability, and support is limited to the Omron hardware. Ultimately, the decision is yours on how to build your machine vision application. After we have selected our lens, we want to set it up and ensure we have an accurate image. If we notice any vignetting or shading around the edges of our image, This indicates we have selected the wrong lens and will need to recalculate to get the correct lens. The goal is to use the maximum amount of available area on the sensor surface.
If further information is desired, we strongly recommend watching the beginning optics for machine vision videos directly through the links below. In addition, we have provided links to short videos outlining the different lens series, their uses, and functions. Thank you very much for learning more about machine vision automation, and we'll see you next time.